Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Lev Davidovich Landau's 1933 paper on the theory of the stars represents a pivotal, albeit initially controversial, contribution to astrophysics. It challenged prevailing assumptions about stellar structure and presaged the discovery of neutron stars and black holes, objects whose existence even the most visionary physicists of the era approached with caution. To fully appreciate the impact of this work, one must consider the state of stellar physics in the early 1930s, the intellectual milieu in which Landau operated, and the subsequent evolution of his eye. Before 1930, the understanding of stellar interiors rested largely on the work of Arthur Eddington. Eddington championed the idea that stars are essentially gaseous spheres held in equilibrium by the inward pull of gravity and the outward pressure of radiation and ionized gas. He developed the celebrated mass-luminosity relationship and explored the role of radiative transfer in determining the temperature gradient within stars. His model, while successful in explaining many observed properties of main-sequence stars, faced difficulties when applied to more exotic objects, particularly white dwarfs. These dense, compact stars, first discovered in the early 20th century, posed a theoretical puzzle. Eddington, along with Ralph Fowler, applied Fermi-Dirac statistics to the degenerate electron gas within white dwarfs, explaining their stability against gravitational collapse. Fowler's work showed that the pressure exerted by degenerate electrons, governed by the Pauli exclusion principle, could support a star against gravity, even at extremely high densities. Landau, however, took a more radical approach. He questioned the very applicability of Eddington's gaseous model to all stars. In his 1933 paper, written swiftly during a period of intense intellectual activity, Landau posited that stars above a certain mass limit, significantly larger than the Chuntiska limit calculated a few years prior for white dwarfs, could not exist as stable degenerate configurations. His argument stemmed from a relativistic treatment of the degenerate electron gas. He demonstrated that as the density of a star increases, the electrons become increasingly relativistic, meaning their speeds approach the speed of light. This modifies the equation of state, relating pressure to density, in a way that weakens the pressure support. Above a critical mass, the relativistic degeneracy pressure becomes insufficient to counteract gravity, leading to inevitable collapse. The specific mechanism of collapse, Landau proposed, would result in the formation of a central core composed of neutrons. He envisioned a scenario where electrons combine with protons, effectively neutralizing the charge and creating a superdense neutron fluid. This concept, groundbreaking at the time, drew inspiration from the recent discovery of the neutron by James Chadwick in 1952. Landau's vision of a neutron core was remarkably prescient. Representing a first theoretical prediction of neutrons, it is important to note that Landau's initial model contained some approximations and was presented with characteristic boldness. He initially suggested a sharp transition at the stellar radius, a simplification that later refinement would address. However, the core idea that sufficiently massive stars could collapse to form ultra-dense objects sustained by neutron degeneracy pressure, or, ultimately, something even more exotic, was revolution. The immediate impact of Landau's paper was mixed. While appreciated by a small circle of theoretical physicists, including Niels Bohr and George Gamow, it faced considerable skepticism from the broader astronomical community, especially Eddington. Eddington remained a staunch advocate of his gaseous model and initially dismissed Landau's conclusions, citing concerns about the treatment of relativistic effects and the unfamiliar physics of neutron matter. The very notion of a star composed primarily of neutrons seemed outlandish to many. It challenged established thinking and required a leap of imagination that many found difficult to make. One important aspect of understanding Landau's influence involved recognizing its connection to the work of Subrahmanyan Chandrasekhar. In 1931, Chandrasekhar, then a young graduate student, derived a similar limit for a mass of white dwarfs, now known as the Chandrasekhar limit. Chandrasekhar's work, initially published in a relatively obscure journal, demonstrated that a white dwarf exceeding approximately 1.44 solar masses, the Chandrasekhar limit, could no longer be supported by electron degeneracy pressure and would collapse. Eddington famously and publicly ridiculed Chandrasekhar's work, primarily because it implied that stars could collapse into objects far denser than white dwarfs, a possibility he deemed absurd. Although Landau's 1933 paper appeared after Chandrasekhar's initial findings, there is evidence that Landau arrived at his conclusions independently. Landau's emphasis on the relativistic effects and the possibility of neutron star formation offered a different perspective on the problem of stellar collapse, even if sharing the same fundamental insight regarding the existence of a limiting mass. The controversy surrounding both Landau's and Chandrasekhar's work highlights the resistance to radical new ideas, within the scientific community, particularly when they challenge established paradigms. The subsequent evolution of Landau's ideas saw further refinement and development. In the late 1930s, Robert Oppenheimer and his student George Volkoff, along with Richard Tolman, independently derived the Tolman-Oppenheimer-Volkoff equation, which describes the structure of a static, spherically symmetric star in general relativity. This equation, often abbreviated as the TOV equation, provides a more accurate description of stellar equilibrium, especially at the ultra-high densities found in neutron stars and black holes. Oppenheimer and Volkoff applied the TOV equation to a model of a neutron star, demonstrating that neutron stars too have a maximum mass beyond which they become unstable and collapse further. This work, published in 1939, solidified the theoretical possibility of neutron stars and established a maximum mass limit for these objects, now estimated to be around 2 to 3 solar masses. While Oppenheimer and Volkoff's work focused primarily on neutron stars, it implicitly paved the way for the acceptance of black holes. The concept of a black hole, an object so dense that nothing, not even light, can escape its gravitational pull, had been considered theoretically by John Michell and Pierre-Simon Laplace in the 18th century, using Newtonian gravity. However, it was Einstein's theory of general relativity that provided the framework for a rigorous understanding of black holes. Carl Schwarzschild obtained the first exact solution to Einstein's field equations describing an unrotating black hole in 1916. The full realization of black holes as astrophysical objects came much later, after decades of theoretical work and observational discoveries. The identification of Cygnus X1 as a black hole candidate in the 1970s, based on its X-ray emissions and inferred mass, provided compelling evidence for their existence. Today, black holes are recognized as fundamental components of the universe, playing a crucial role in galaxy formation and evolution. Landau's 1933 paper, while not directly predicting black holes, provided a crucial stepping stone in their eventual acceptance. By challenging the prevailing assumptions about stellar structure and proposing the existence of neutron stars, Landau expanded the realm of possibilities for stellar endpoints. His work prepared the ground for the theoretical developments that followed, including the TOV equation and the eventual understanding of black hole physics. The enduring legacy of Landau's on the theory of the stars lies in its boldness, its prescience, and its profound impact on our understanding of stellar evolution. It demonstrated the power of theoretical physics to challenge established paradigms and to anticipate new discoveries. Landau's work, despite initial skepticism, ultimately revolutionized astrophysics and paved the discovery of some of the most fascinating and enigmatic objects in the universe. The paper also indirectly fostered a deeper appreciation for the limitations of classical physics when dealing with extreme gravitational fields and ultra-dense matter. This realization propelled the development of more sophisticated theoretical tools, including numerical simulations and advanced relativistic calculations, which are now essential for studying neutron stars and black holes. Furthermore, Landau's work served as an inspiration for generations of physicists and astronomers. It exemplified the importance of intellectual curiosity, the courage to challenge conventional wisdom, and the pursuit of fundamental understanding, even in the face of uncertainty and skepticism. His contributions extended far beyond the specific topic of stellar structure, influencing the development of many other branches of physics, including condensed matter physics, superfluidity, and plasma physics. It is perhaps ironic that Landau, who initially envisioned neutron stars as the ultimate fate of massive stars, did not fully embrace the concept of black holes. He remained skeptical about their existence, possibly due to the mathematical singularities associated with them in the early formulations of general relativity. Nevertheless, his pioneering work on stellar collapse played a crucial role in the eventual acceptance of these exotic objects. He established the conceptual framework upon which future research could build. In conclusion, Landau's 1933 paper on the theory of the stars stands as a testament to the power of theoretical insight in unraveling the mysteries of the cosmos. It demonstrated that the seemingly stable and predictable world of stars could harbor objects of unimaginable density and exotic physics. The paper, though initially controversial, ultimately revolutionized our understanding of stellar evolution and paved the way for the discovery of neutron stars and black holes, cementing Landau's place as one of the most influential physicists of the 20th century. This legacy continues to inspire and challenge scientists to explore the frontiers of knowledge and to push the boundaries of human understanding.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.